Challenges by Dr. K.G. Sharma, Associate Professor, CCET, Chandigarh.
Hello everyone. So today we are going to discuss about the VLSI issues and design challenges. So first of all, if we like to understand what are the interesting facts about the VLSI, basically we will start from the basic of the VLSI evolution, and then we will move to the recent advances in VLSI and how the research and everything is going on today. So first of all, the interesting facts about the VLSI we talk about 30% of all the electronic component consist of semiconductor components.
Hello.
And about 20.
Hello. Your voice is not audible, sir. Voice is not coming.
And about 20% of all ICs are ASICs. Am I audible? In the year 2000, the world production of semiconductor components was around $300 billion. If we talk about nowadays, it is more than $40 billion. Channel length, which was 0.13 micron in the year 2000, reaches to 10 nanometer nowadays. So these are the interesting facts if we talk about. Now next is, we talk about the advantages of integrated circuit over the other circuit technologies, like if we suppose make the circuits in a discrete components using discrete components, as well as suppose we fabricate the thing in a breadboards. If we talk about advantages, then cost is the one of the advantage of integrated circuit, and this is because of the batch processing. If suppose we have to make one single IC, the cost of that IC will be very high. But if there is the batch processing production in millions ICs per year, per day, so cost becomes very low. Reliability is the next advantage. So in discrete circuit, there is problem of loose connection. But in case of ICs, once the IC is fabricated, these kind of loose connection, open circuit, short circuit, these problems will not be there. So reliability is one of the factor. Another factor is the speed. Since in integrated circuit, the components are very close to each other, so the speed of the ICs is also very good. Another is low power. Since the components are placed closer to each other, so because of that, you can say that power consumption is low because small interconnections are required. So after the advent of IC development technology, more research started to embed more transistors in a single wafer, and then in 1970, microprocessors were developed. So microprocessors are nothing but a CPU of a computer. Next is IC classification. If suppose we divide the ICs in different categories. So first one is ASIC, application specific integrated circuit. So these are specific ICs for particular applications like hearing aid, cell phone, TV controller, game developments, and so on. Anything is specific for one application and cannot be used for other application. These are ASICs. This concept became very popular when volume sales is required. For example, cell phone production. In cell phone, we require some ASICs, and these are meant for mobile phones only. Next is FPGAs, field programmable gate array. These are similar to the digital signal processors. They are programmable. DSPs are reprogrammable and can be used for different processing application, but FPGAs are programmed for specific applications. FPGAs became popular for small scale applications, prototyping, university research, and so on. Develop program with the software tool, upload to FPGA, and then we can run and test the device. So in general, if suppose we say FPGAs are more and more used towards the university research and applications, where you can see your program or your design in a real-time functioning. Next is system on chip, SoCs. So in this case, entire computer is fabricated on a one single chip. For example, input, output, memory, DMA, they are fabricated in one chip. People call them as embedded system. So nowadays, embedded systems are also very much growing field. If we talk about evolution, so the transistor was first fabricated in Bell laboratories in 1950s. In 1960s, integrated circuits came into the existence where more number of transistors are utilized to make one or two circuits. In 1970s, microprocessors came into the existence. In 80s, digital signal processors. In 1990s, ASICs and FPGAs came into the existence. And in 2000 onwards, system on chip. So if we talk about the first computer, that was the Babbage, that was working on a difference engine operation. So executed basic operations like addition, subtraction, multiplication, division in arbitrary sequences. And it was very, very huge computer. And it operates in two cycles. One is store, another is execute, that is mill. Included features like pipelining to make it faster, complexity around 25,000 parts, and cost was around 17,470 pounds in 1834. You can think of it was very, very huge cost at that time. So dawn of transistor age, it means transistor came into the existence in 1947 when Bardeen and Brattain create point contact transistor with two PN junction, and gain of that transistor was around 18. In 1951, Shockley developed junction transistor which can be manufactured in quantity. And that was starting of the integrated circuit era. First electronic computer was developed in 1946, and that was ENIAC. Early integration, if we talk about, then Jack Kilby, working at Texas Instrument, invented a monolithic integrated circuit in July 1959. He had constructed the flip-flop shown in the patent drawing above. In mid-1959, Noyes developed the first true integrated circuit using planar transistor, back-to-back PN junction for isolation, diode isolation, silicon resistor, and SiO2 insulation with evaporated metal wiring on the top. In 1970, Intel started selling a 1 kbit RAM that is numbered as 1103, and its density and cost make it only game into town. It means it was very, very popular at that time. In 1971, Tedoff at Intel designed the first microprocessor, and that was 4004, and that had 4-bit buses and a clock rate of 108 kilohertz. That was the first microprocessor, and it has 2300 transistors and was built in 10 micrometer technology. You can compare with the latest technology nowadays. It is 2300 transistors. These are very, very less in comparison to an IC. So first 30 plus year, if we talk about, first of all, there was Intel 4004, and it was developed or came into the existence in November 15, 1971. And it was having 4-bit ALU and working at 108 kilohertz, around 2300 transistors, and 10 micron technology. Intel Pentium 4 came into the existence in August 27, 2001. 32-bit architecture, 1.4 gigahertz clock cycle, 42 million transistors. Even nowadays, it is much, much more than 10 power 7 transistor on chip. Then 0.18 micron technology was used. And nowadays, if we talk about, we have a 10 nanometer, we are working on a 10 nanometer technology. So during this 30-year, Moore developed a law of design and productivity gap. They produced one curve, and they had shown that productivity or designing of larger designs cannot be increased with the same pace of the transistor size shrinking. It means production rate and the transistor size shrinking, almost they are mismatching, but they said the number of transistor per chip double in every 18 to 24 months. So motivation for scaling. Basically, what happened after the advent of the IC technology, everyone started working on embedding more and more number of transistors on a one single chip. So to do this process, the need of scaling arrived. And motivation for scaling was more number of transistors can be embedded on a one single chip. And because of that, the higher performance can be achieved, as well as more functionalities can be achieved. Because of this, as the devices are coming more and more closer, the delay time was reducing. And because of that, the higher frequency applications were achieved. And obviously, the design size is shrinking. Because of that, the supply voltage requirement was also very less. So low power consumption was the main idea behind this motivation. So scaling is basically, if we just formate a one rule, so we can say technology shrinks by 0.7 per generation, not now, but it was earlier predicted. With every generation can integrate 2 times more functions per chip, and chip cost does not increase significantly. If suppose we talk about the cost of the microprocessors, it is basically in every 6 months we are saying that the microprocessor is now obsolete, but cost is not so much changed. Cost of the microprocessor, latest microprocessor, is almost comparable with the earlier microprocessor or microcontroller. Cost of a function decreases by 2 times. But how to design chips with more and more function, that was the challenge. Design engineering population does not double every 2 years. That was the contradiction towards the Moore's law. Hence, a need of more efficient design methods were to be developed, and the research started on this and exploit different level of abstractions. So if suppose we talk about the number of layers on a one single IC, these layers are up to 11 layers of metal layers that is there. But more than that, if suppose it is required, it can be done, but that is going to increase the cost. So challenges for MOSFET scaling was the CMOS technology has been a basic key for continuous progress in silicon-based semiconductor industry. Scaling is followed by Moore's law since few decades, which provided simple rules for transistor design to increase circuit density and speed. However, our device scaling continues for the 21st century. Doubled circuit density and increased performance followed by Moore's law cannot be maintained only by the conventional scaling theory. Power supply and threshold. The MOSFET scaling tends to involve a reduction in supply voltage to keep electric field and power dissipation within the limit. If suppose we have to scale down, we have to shrink the size of the MOSFET, we cannot continue with the same applied voltage. It means if suppose earlier in early days 5 volt was the supply voltage, and now the design is having the 10 nanometer or 14 nanometer technology where channel length is 14 nanometer, and also the thickness of the gate oxide is also very less. So if suppose we apply 5 volts, the electric field will be hazardous, or you can say very, very, very high. And because of that, what will happen? The device will break down. So along with the shrinking of the devices, the supply voltage and electric field are also required to scale down. But there are other challenges also. But the threshold voltage cannot be scaled down too much. So when we operate in sub-threshold region, then leakage current constitutes a significant portion of the total power dissipation. So in sub-threshold region, basically what we do, we decide the logic levels within the sub-threshold levels. It means all the power supplies and the input voltages are kept below that, are kept below the threshold voltage. And the leakage current is basically the deciding factor. And in that case, static power dissipation and dynamic power dissipation were very, very negligible, and only the leakage power dissipation is there. High electric field. The supply voltage cannot be reduced with the same pace of the channel length. Hence, the scaling will increase the electric field strength across the gate oxide, and in worst cases, it can cause the breakdown of the barrier, as I told you earlier. Gate oxide tunneling. Scaling of MOSFET requires appropriate reduction in gate oxide. The thin oxide films subject to quantum mechanical tunneling, which give rise to is exponentially increasing the leakage current. So that is also another problem. Further scaling can be realized by replacing the oxide gate oxide material with the high permittivity or high K dielectric material. It means earlier it was silicon dioxide as a gate material. Nowadays we are using hafnium oxide or tantalum oxide and other material for the gate oxide fabrication, so that the thickness of the gate oxide is very, very less, but along with that high K factor, other problems are slightly reduced. It means SiO2 is having around high K of 5 around, so, but high K gate that is having around 25 or more than that. Parasitic resistances and capacitances. As the transistors are scaled down, influence of parasitic resistances and capacitances on current increases significantly. Another challenge is hot carrier effect. When carriers possess high energies, having effective temperature greater than the lattice temperature, they are said to be very, very hot or very, very energetic. The main problem which arises due to hot carriers are parasitic gate currents, drain current degradation, decrease in transcurrent conductance, GM, and shift of threshold voltage with time. Using graded drain profile reduces the problem of generation of hot carriers. Randomness in dopant distribution. As the device dimensions are reduced, it becomes difficult to place the dopant atoms at exact and required position, and that may create some diffusion problems, or you can say that may create, if suppose there is non-uniform doping of the material, that creates a problem. Source to drain tunneling. If the MOSFET channel length between source and drain becomes small enough, it can no longer be operated as a switch. Heat dissipation. If the heat dissipation is not proper inside the chip, hot spots are created on the circuit, which causes malfunctioning of the device. So whenever we are fabricating any chip, we have to ensure that the areas, or you can say the circuits which are requiring or which are dissipating more and more heat, that has to be uniformly placed. In that case, we have to have the trade-off with the speed and the interconnection complexity, but we have to place them in a uniform manner, so that not only one area of the chip is containing whole of the highly power dissipating elements. Interconnect delays. So reduction in wire width increases the resistance, hence increases the delay, and this also reduces the speed. Short channel effect. Basically, there are so many short channel effect, but one is a drain induced barrier lowering. We'll discuss later on this issue also. Technology practical difficulties are the people are running out of tricks to enhance lithography method. So because of that, there is a problem of phase shift. Etching tricks are very less. So obviously problem is arising. Complex designs are not limited by devices, but by wiring. It means we are decreasing the size of the transistor, but at the same time, we have to think about that how we have to connect all the transistors on one single chip. So complex designs are limited by the device, not limited by the devices, they are limited by the interconnections. High-end design will require around 12 metal layers. So if we talk about the microprocessors, they may require 12 metal layers to interconnect all the devices which are fabricated on the IC surface. Considerable higher cost. So as you have to fabricate a very, very complex design, complexity increases the cost. One of the other major concern is power. So MOSFET channel downscaling tends to involve proportional reduction in supply voltage to keep electric field and active power within limits. So power is a very, very challenging situation every time, and we have to consider that otherwise we will not be able to fabricate any efficient chip. If you talk about the mobile phone, not only microprocessor but other devices designed design is also require concern towards the power dissipation. So if we talk about digital cellular market, basically up to 2000, it has started from 48 million in 1996, reached to the 435 million in 2000. It means within the 4 years, 10 times increase is there in the selling. Interconnect restrictions. So while not directly related to the silicon technology, wires represent a fundamental problem in a miniaturization of the circuits. So as transistors continue to shrink, wires and interconnect do not shrink at the similar pace. However, more and more wiring is needed to connect the increased number of transistors. That is a problem. Problem with the decreasing width of the wires. So increases resistance per unit length. A smaller cross-sectional area means increased resistance. Capacitance inversely increased, leading to a constant RC times. As circuit speed increases, this leads to a transmission delay limited by the RC time constant rather than velocity of the electromagnetic waves. Currently, if we talk about the density of the current density increases as cross-sectional area of the wire decreases. And as the technology is enhancing, the width of the wire is decreasing. Because of that, the current density is increasing. And we have to take care of the current carrying capability of the interconnects also. So we cannot decrease the width of the wire with the same pace. Current density is limited by the electromigration, the movement of atom by the electric current. So there may be some problem like open circuit failure can be there, or short circuit failure can be there, if suppose we are not taking this into the much concern. Problem with the longer wiring. So if suppose we have the device, one device at one corner of the IC and another device at the another corner of the IC. So in that case, a longer wiring is required. But as you know that as the signal travels in the medium or in the wire, there is some, that's the first. So as the signal travels in a wire or medium, it suffers attenuation. So to decrease this problem, we have to ensure that some of the repeaters has to be there, or some of the buffers has to be there in the mid. So it requires layering to separate each trace. And it leads to a higher production cost too. And result is that production limits are sometimes restricted by monetary barriers, not technological limitations. Planarization. This is also becoming a very, very stringent problem, that if suppose we have a big wafer and we have to construct a very small IC out of that, if suppose that the surface is not planar, then helix formation or other kind of problems can be there in the surface, and that is going to reduce the efficiency of the devices. So how much flat that wafer is, that is very, very stringent if we are working on a 65 nanometer and below technology. So wafer planarity has to be 10 to 50 nanometer. It means that any layer cannot have more than that height or depth. And if we compare with the soccer field planarity, it is 5 to 25 micrometers. So it is very, very stringent criteria to maintain such flatness. Next is high leakage current. So 5 major sources of leakage current are gate oxide tunneling leakage, subthreshold leakage, reverse bias junction leakage, gate induced drain leakage, gate current due to hot air carrier injection. It means as the device size is shrinking, as the technology is advancing, and these leakage currents are coming into more picture. So if we talk about the current research trends, First of all, talk about the graphene. Up to now, we talked about the basic evolution of the ICs. Now we talk about to overcome such problems, how the technology is increasing. So in 2003, graphene was discovered. Graphene is nothing but a very, very one atom thin sheet of carbon atoms, and that are arranged in a hexagonal format, that is in a 2D structure. So it is having very, very extremely high electron mobility, around 25,000 centimeters square per volt per second. And as well as along with that, it provides high thermal conductivity too. It means 3,000 to 5,000 watt per millikelvin. So graphene is, more and more research is going on in graphene. And suppose if we can design any transistor using graphene, then it is going to change the direction of the technology. It means we will switch from the semiconductor to the graphene technology. But still, we are not having such kind of thing. So it is basically used for making a strong and durable touch screens for the smartphones and also for the monitors, solar cells, pressure sensors, and state-of-art monitors. So till date, it is not, we cannot use this device for the fabrication of any transistors or MOSFETs and so on. And that is limited because of its feature. So, but still, it is very much popular nowadays. And we are fabricating, or we are making use of this in different areas like touch screen fabrication, solar cells, pressure sensors, and monitors. Advantage of this graphene is that it is a thinnest and strongest known material, which is harder than diamond, even 2,500 times harder than steel. And it is just a thin sheet of one atom. And it is a 2D structure. It is superconductor of the heat and electricity. So if suppose in any application, if heat or power dissipation or such kind of activities are degrading the performance, then this material is going to be a very, very popular. Used in lithium-ion batteries that recharge faster. And in these batteries, graphene is used on the anode surface, and that is going to resolve the problem of recharging. But the disadvantage associated with this graphene is it does not have band gap, hence cannot act as a switch. And this is the main problem nowadays, how to increase the band gap. Because if suppose we want this material to act or to work as a transistor, or we can make transistor using this material, then there should be a band gap. And that band gap should be around 1 electron volts, not less than that. Susceptible towards the oxidation environment. It is highly reactive towards the oxygen. So it is again the criteria that if suppose you are making any device using this material, it cannot be exposed in the environment. Samsung is leading with IBM and Xerox with 210 patents in this graphene. Following mechanism can be used to create band gap in the graphene. Number one is by applying the electric field. Second one is doping with atoms. And third one is stretching and squeezing the atoms. Nowadays, third criteria or third thing is used to create the band gap. Work is going on. Practical digital circuits require a band gap on the order of 1 electron volt at the room temperature. If suppose we want to design any digital circuit or any kind of circuit where we have to decide 0 and 1 level, so it is required that it cannot be less than 1 electron volt, or around that. A small variation may be there. It will be acceptable, but around 1 electron volt. Graphene transistors can operate at a very, very high speed of 400 gigahertz. So if suppose we can be able to make any transistor using this graphene, obviously we will have a very, very revolutionary change or revolutionary advantage towards the speed of the operation of the devices. Research is going on to increase the band gap. So Institute of Basic Sciences in South Korea is working on bridge type reaction to increase the band gap of the graphene. And in this process, lithium is dissolved in ammonia to create the CH bond. And because of this creation of the CH bond, stretching or squeezing of the surface will be there. And because of the that band gap of the material changes. But still, till date, we have not reached 1 electron volt. We have reached only 0.1 electron volt till date. So we can think of that creating any transistor using graphene is not possible till date, but hope that in future we can be able to make use of this graphene. Cost is another disadvantage factor if we talk about, because why we use silicon in fabricating the ICs, even though we have other semiconductor material. We all know that silicon is abundant in nature, and because of that, its cost is very, very low. So making an IC using silicon material is cost effective. And that is one of the advantage that we are using silicon till date. So if we talk about the cost, electronic grade silicon, EGS, is sold at the rate of $50 per kg, while graphene, if we are making graphene and processing and everything, if that is involved, then it is $40,000 per kg. So till date, if suppose we are able to fabricate transistor using graphene, still this is going to be a biggest issue. And application of the graphene they are used in sensors, batteries, and electron emission displays. Next area which is working, the research is going on, working on a strained silicon. So silicon material in which silicon atoms are stretched beyond their normal interatomic distance, and basically it is accomplished by keeping a layer of silicon over the substrate of silicon G. Basic thing is there that if suppose we have a layer of any material, if suppose we are forming any heterostructure, then in that case the crystalline structure will be slightly changed. It will not be as that from top to bottom the same crystalline structure is there. So whenever there is an interface between the two material, at that interface the bond length changes. And that can be understood with a very, very small example, that if suppose we have a jar, a glass jar, and we are placing the bigger balls over there, and then we start placing the smaller balls over the bigger balls, then they start acquiring some random type of locations, and because of that you can say at the interface the distance between the balls are also not same. On the top and on the bottom, that is having some regular structure, but not at the interface. The same kind of phenomena is there, and because of that the silicon interface, silicon and silicon germanium interface is slightly stretched, and because of that some specific properties are achieved. And due to this reduced atomic forces between stretched silicon atoms, better charge mobility is achieved. So if suppose in a material, if suppose we are increasing the distance between the atoms, then what will happen? Because of the stretching of the atoms, because of the increased distance of the atom, the atomic forces will decrease, as well as more and more area will be provided for the electrons to move through. So because of this, the charge mobility, better charge mobility is achieved. It means the speed of operation increases. So electron can move 70% faster, allowing strained silicon transistor for some specific pattern. And because of this, transistors will switch 35% faster. So that is the overall increase in the speed of the operation of the devices which are using the strained silicon. But it is also having very, very other type of problems in fabrication that we are not going to discuss. So in 2015, around 3.5 billion are expended on strained silicon devices. and nearly 66 companies worldwide are manufacturing such devices. Next is high K metal gate. It means we earlier talked about that as the device size is shrinking, as the material, gate oxide material thickness is decreasing, the same SiO2 is not giving you the proper design efficiency. So now in 2012 and onwards, basically the scientists started thinking of that, can we decide the high K metal gate? So the new materials which are used in place of SiO2, one is zirconium oxide, that is having K of around 25, and hafnium oxide, that is having K of around 25. So in zirconium and hafnium oxide, if we talk about, zirconium oxide is slightly reactive towards with the silicon. So it is creating problem when we are making any gate oxide material. So the interface is not becoming or coming out to be proper in case of zirconium oxide, but hafnium oxide is giving the proper result. So it is having the high K value as well as chemical stability with the water and silicon. Another is single middle gap metal. Basically, we can have two types of technology, that single mid gap metal and double mid gap metal. So in single mid gap metal, VT is almost constant. It means same type of metal is used to fabricate PMOS and NMOS, and symmetrical processing steps are there, simpler processing steps are there, and as well as symmetrical VT, the threshold voltage is same for NMOS and PMOS almost. But high VT and compensation implants degrade channel carrier mobility. That is the disadvantage associated with the single mid gap metal. Another possibility is that there is a dual mid gap metal approach. So in this case, separate metal is used for PMOS and NMOS. So feasible metal electrode for NMOS, that is aluminum, tantalum nitride, and conducting metal oxide is iridium oxide. While in the case of PMOS, feasible metal electrode is platinum, and conducting metal oxide is ruthenium oxide. So, and also metal is used. Now you can just think of that why I'm talking about the iridium oxide and ruthenium oxide used as metal oxide. So metal gate is now becoming popular. It means earlier we were using the polysilicon gate. Now we are moving again back towards the metal gate. And because of this, because you can think of the problems or the solutions are there, less amount of defect at the surface. If suppose we are using the polysilicon, then more and more defects were there at the interface or at the surface. Similarly, and again, point is effectively no depletion layer formation is there. If suppose we are using polysilicon material, then depletion layer is formed. But in case of metal, if we are using aluminum or tantalum and titanium nitride or platinum in PMOS, then no depletion layer formation will be there. Along with that, less resistant compared to the polysilicon. So polysilicon is basically heavily doped polysilicon material is used in place of the metal gate or metal technology earlier, but still the resistance was slightly more than the metals. So less resistance compared to the polysilicon material. And another way we talk about next is the MOSFET evolution. It means along with the different technologies we are using, conventional MOSFET structure is also changed. So earlier, if we talk about the conventional MOSFET structure in which gate was there, then silicon substrate was there. Over that, we are making the gate, drain, and source. So as we are decreasing the size of the MOSFET, it means channel length. Basically, there were so many short channel effects, so many problems were there that we'll discuss in the next lecture. And one of the effect was DIBL effect, hot carrier electron effect, and so on. Because of that, the saturation was there. It means further we were not able to decrease the size of the MOSFET below 22 nanometer or 20 nanometer. So again, the research started of thinking of how to reduce these kind of problems. So next, the design came was SOI, that is silicon on insulator. It means instead of keeping hole through substrate below the device, one insulator is kept in the mid between the device area and the substrate. And because of this, the formation of the capacitance or formation of the diodes with the gate and source and drain region with the substrate. Now, in this case, that is not possible in the case of SOI, and that problem is highly reduced in this case. But still, we were not having very, very high control over the electrostatics in the case of planar SOI surface. So the design moved to another kind of approach, that whether we can use the double gate type of technology in which the channel will be heavily constrained and the current will be heavily controlled. So gate is now on the two sides of the channel. But still, the research was continue, and then it came with the another design, which was FinFET, and this is basically the 3D structure in which we are not fabricating each and everything below the surface. We are fabricating above the surface also. It means the channel, source, and drain, they are now above the channel, above the surface of the SOI, above the surface of the substrate. So in this case, we can also have the two kinds of possibility, that we can have the SOI type of surface, or we can have the conventional planar surface. Both designs are possible. We'll discuss about the FinFET structure, and then we'll talk about which are better, in which case which is better. So in this case, we are having a channel above the surface. And since it is creating a very, very similar structure like a fin, that's why it is termed as FinFET. And it is basically like that top of the fin is not providing any control. Only side of the gate or side of the fins are controlling the current which is flowing in the channel. After that, tri-gate came into the existence. It means all the three surfaces of the gate, top and side surfaces of the gate, they are given the gate voltage, and the current is more and more controlled. Electrostatics become more, even more controlled. But still, the research is going on, and so on. We reach to the pi gate, where the gate material is slightly more extended towards the surface of the wafer, and we are having more control. And then ohm gate is there, which is having a sign of ohm sort of, and in this it is covering more and more channel area and giving more control over the electrostatic. And then came with the design of a gate all around. It means whole of the channel is covered all around by the gate surface. In this case, you can think of so many problems are removed. If we talk about the gate all around, though it is a very, very complex type of structure and fabrication is very, very difficult in this case, still not fabricated any device on gate all around the structure. But you can think of, in this case, we have the better control over the electrostatics in this case. So that's all now. And you can ask any question if you have on this whole presentation.
Hello, sir. Nitika from Manarachna University.
Yes, please, ma'am.
So you said that the materials replacing the silicon dioxide
SiO2, that is ZrO2 and HF02.
Yes.
How is their adhesive is compared to SiO2?
Obviously, you can think of there is a problem, because whenever you are moving to other technology, problems will be there. That whenever we talk about the SiO2 and silicon, obviously silicon material is there, so the interface becomes uh, very efficient, you can say, or you can say very much good interface can be created. But still SiO2 and silicon, they're also different material, so heterostructure is also always there. So in that case, you can think of just at the interface, the atom placed, they have slightly disturbed. They will not have the same structure continue. So with SiO2 even we have the same problem, that adhesiveness is not proper. Same problem will be there with the, or even more problem will be there with the zirconium or aphinium oxide or any other material we are going to use. So it is not like that if suppose we are placing the atoms just below and suddenly it will be removed because of anything. So that adhesiveness will be there because bonding will be there. If bonding between the upper layer atoms is there with the lower layer atom, then obviously the structure is good.
Thank you, sir.
Okay, sir. Good morning, sir.
Good morning.
So my name is from Manarachna University. Sir, I have a small query. I don't have a doubt, but I have a small query that in case if we are using ZrO2 or HFO2, what will be the effect on interface and oxide charges, sir? It will increase or decrease?
Again, the same thing I am going to repeat. You have to just imagine the whole of the scenario. That
Yes.
if suppose we are having a surface of silicon, over that we are laying the surface of SiO2 or ZrO2 or HFO2, then obviously at the interface the structure will be suffering with the some you can say some interatomic distances will not be same as you are expecting with the solitary material. So if suppose HFO2 is there, so you can think of HF atom is there, it is having bond with the two oxygen atoms, and now that is placed over the surface of silicon only, silicon which is having silicon bonded with four silicon neighboring silicon atoms. So when hafnium oxide or oxygen is there and that is making bond with the silicon, obviously that is very possible because silicon is also very much susceptible or reactive towards the oxygen, so that is going to form the bond with the oxygen. But overall structure, because the size of the hafnium is not same as silicon, size of oxygen is not same as silicon, obviously the structure will be slightly disturbed. So that bond length, or you can say that interatomic distances will be different.
Okay. Thank you, sir.
Okay. Any other query?
Any other query from any other nodal center?
So we are going to start our session after 15 minutes. 11 o'clock. Okay. So at 11 o'clock, we are going to start our next session, and in which we are going to discuss about the FinFET devices. Thank you all. Normal पानी है आपका नाम
Oh, I am a student of MTech. College. Hello. Huh? Why follow? मैं उधर आ रहा हूँ ये क्या बना रहा हूँ कौन सा अभी ठीक है देखा नहीं है क्लास में आया था इधर क्लास में नहीं जा ठीक है कौन सा वो कॉलेज वाला भेजा है कौन सा भेजा हाँ बताओ कौन सी अच्छा 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 हाँ यार इसके बाद नहीं अब अपने कॉलेज के बच्चे हैं ना उनकी फीस कम होगी 1000 रुपये हाँ अरे वो इंटरनेशनल कॉन्फ्रेंस वही हाँ इंटरनेशनल कॉन्फ्रेंस है तो वैसे हाँ इंडिया तो होगा इंडिया तो होगा हाँ वैसे भी बस तो हमारे पास अगर डी की लैब बच्चे अभी 10-50 से लगे उन्होंने सबको मुझे लग रहा है शायद बच्चे हैं नहीं शायद 10 हैं तो अगर लैब लगी तो 12 बजे से 12 बजे आ जाना। हाँ नरेंद्र से पूछ लेना मैं 12 बजे कर रहा हूँ। वो गूगल को उसके पानी को निकलवा देते खाना निकाल देता पानी को फिर ताजा पानी भर देता उसमें उनको बाहर को निकाल देना उसमें से डायरेक्ट वगैरह मतलब लगे नहीं होने चाहिए। ठीक है वो कहीं प्लग लगा हुए में और ये निकालने लग जाएगा। अंदर बात दिमागी बात में आके उससे देख के ध्यान दूसरे कहीं के लगे हुए को नहीं निकाल दिया तो और
Good morning, participants. So we're going to start our second session of the day, FinFET Design by Dr. KG Sharma. So, and in continuation of this lecture, at the end of this lecture, we will proceed for the valediction of this course. So I request all the centers, please be there for the valediction of the course. Thank you.
Hello, everyone. So now we have to start with another lecture on FinFET design. So first question that comes in our mind, why FinFET? It means earlier we were having already the conventional MOSFET structure. We are very much known with that structure, with the very much familiarized with the equations and everything. So why to switch on to the another technology or another kind of structure? So basically we are first going to discuss about why FinFET, then we will move towards the fabrication and the challenges with the FinFET design. So as the process technology is increasing, manufacturing of FinFET and tri-gate transistor, we need to get brief motivation why there is a need of tri-gate or FinFET or fully depleted kind of devices. So what is the need to move from planar MOSFET structure to FinFET or tri-gate structure? So first of all, we talk about what is the problem coming with the short channel devices. So first of all, if suppose we talk about the planar structure of the MOSFET, and in that planar structure, there can be two possibilities. One is the long channel MOSFET and another is short channel MOSFET. So first of all, talk about the long channel MOSFET. In that kind of device, if we talk about source to drain region, then there is a barrier. That barrier is created because of the change in the band structure. So from source to drain, if suppose we want to create a channel, we have to provide some gate voltage. Or in other words, we say that the electrons see the barrier, but this barrier reduces with the gate voltage. So as we increase the gate voltage, the barrier is lowering, reducing from the, and there will be the motion of the electron from source to drain. And if we just see this curve in the case of long channel MOSFET, that is ID versus VGS curve. So as we increase the gate current, similar kind of increase will be there in the subthreshold slope as well as in the drain voltage. It means, say if suppose there is an increase of the gate current by 100 times by increasing the gate voltage or by increasing the drain voltage, in general you will see with the curve that there is an increase of subthreshold slope. There will be the increase of the drain voltage by the same amount. So if there is an increase of 100 times drain current, then there will be increase of 100 times drain voltage, keeping the subthreshold voltage constant as well as the threshold voltage constant. So in long channel MOSFET, if drain current increases n times, then there is n times increase in drain current in off and on state, as well as slope remains same. So in case of long channel MOSFET, these are the basic points we have to remember, that threshold voltage remains the same, subthreshold slope remains same, on and off current increases with the drain voltage in the same proportion. Now come to the short channel MOSFET. So in short channel MOSFET, at low drain voltage around VD is equal to 10 millivolts, things are same as long as in case of the long channel MOSFET. So barrier is lowering with the help of gate voltage. So as we are increasing the gate voltage, the same increase in the current and subthreshold slope will be constant in that case. But if we increase the drain voltage from VD to 1 volts, it means if we increase the drain voltage by 100 times, then barrier also lowers with the applied drain voltage. And this effect is termed as drain-induced lowering effect. So this is DIBL effect. So you can think of that in this case, the subthreshold slope as well as the drain voltage difference will be slightly unexpected, or you can say undesired one. So it means barrier for electrons to flow from source to drain is not only affected by the gate voltage, but it is also affected by the drain voltage. So just see that curve, that if the drain current is increased by more than 100 times, then you can see that the drain current is, drain voltage is not increasing with the same amount. Also the subthreshold slope is changing. Along with that, you can see there is a change in the threshold voltage. So by changing or by moving from long channel MOSFET to short channel MOSFET, there are some degradations. So in short channel MOSFET, if drain voltage is increased 100 times, then on current increases 100 times, but off current increases even more than 100 times. Because of this decrease in barrier at high drain voltage. Along with that, threshold voltage also shifts with the application of the drain voltage. And this is not the desired criteria, desired thing. So if we summarize that, we have mainly three short channel effect in MOSFET. Number one is DIBL. And because of that, there is the change in the threshold voltage. Another point, sub-threshold voltage slope changes and off current increases. So you have to think about that if we do not want such kind of degradation or undesired things in a structure, in a device, then we have to think about another kind of device which can possibly reduce this problem. So possible options are, so all these short channel effects are bad for the devices and the circuits. All these effects are lowering the gate control over the current flow. So if we can add more gate, one above and one below, that is the possibility of double gate MOSFET, or put gate at the side also, that is tri-gate MOSFET, or put gate all around, that is gate all around, then control over current flow can be increased. So the difference between FinFET and tri-gate devices is that in FinFET device we have two gates only, and we don't use top surface of the gate. While in the case of tri-gate, top surface is also utilized. So in case of FinFET, basically the top surface have thin silicon nitride layer, and because of that thick silicon nitride layer, and because of that the top surface, the voltage applied at the top surface will not affect the channel current. So Intel and TSMC announced that they will be using tri-gate device beyond 20 nanometer technology. But there are also some foundries still exploring FDSOI, fully depleted silicon on insulator. But they're still working on that, improving the characteristic so that the conventional design can be still used to overcome the problem and to reduce the possibility of the problem. But Intel, TSMC, and some other foundries already switched to the tri-gate and FinFET devices. So FDSOI is also still an option to fabricate MOS transistor. But if we talk about Intel and other big giants of the fabrication companies, then now we are shifted towards the other kind of device option, that is FinFET or tri-gate. Even 14 nanometer technology using, if suppose you are using iPhone and other devices, they are utilizing the 16 and 14 nanometer technology. They are basically using the tri-gate and FinFET technology. So FinFET technology market is estimated to reach 32.74 billion by 2022 at a CAGR of 28.6% through the forecast period. This growth in the FinFET technology market is due to the increasing IC industry, which is proving ample growth opportunity to the FinFET technology market. So in general, if suppose we compare the planar MOSFET with the tri-gate technology, so tri-gate is basically decreasing the off current and providing the better sub-threshold slope. Body shape of FinFET, it can be like that you can see that fin is containing the channel part, and gate oxide is all around wrapped, and there can be possibility of double gate structure, and there can be possibility of the tri-gate structure. So in case of tri-gate structure, you can have the 90-degree corner, or you can say half circle corner. We'll see later on why we are providing such kind of the kind of cornering or removing the edges, and what are the problems associated with that. That we'll see later. So schematic view of DG MOSFET, that is bulk FinFET or SOI FinFET. In this case, you can see that there are so many things we have to consider when we are working on such kind of devices, and how the parameters of devices are basically constituting the current and other things. In FinFET device, basically the design consideration includes fin width, which is going to determine the DIBL effect, fin height. It is basically limited by the H technology. We have to discuss. Trade-off will be the layout efficiency and versus design flexibility. And third one is fin pitch. That is going to determine the layout area, which is basically limiting the SD implant tilt angle. And trade-off is performance versus the layout efficiency. If suppose we need to model the side channel VTH or the side channel, then you can see that the different parameters are there, and on the basis of these parameters, you can constitute the threshold voltage or change in the threshold voltage with the different kind of parameters like charge sharing length and others. And the VTH modeling of side channel, you can see in narrow width channel, VTH is there, and depletion width is also, you can characterize, you can see the formula for that. And all the parameters which are basically utilized in this are the fabrication along with the fabrication parameters, and on the basis of that you can think how the threshold voltage is characterized. FinFET layout, in general, if you see that in a chip surface, we are not going to construct one single fin and over that we are making a gate wrapping around and then forming a source and drain region and utilizing one. We are basically using a number of fins, and we are applying the gate over all the fins, and then we are applying the source and drain and other things. So layout is similar to that of conventional MOSFET, except that the channel width is quantized. Bulk and SOI FinFET, if we talk about the differences, in the case of SOI FinFET, the silicon surface over that oxide surface is laid, and then fin is grown over that oxide, and then gate is wrapped all around and source regions are made. So there is no contact of the fin with the bulk substrate. While in the case of bulk FinFET, the fin is directly connected with the surface of the bulk. So device engineers around the world are struggling to make FinFET on SOI substrate or on bulk substrate, and they are just trying to find out what are the different application and advantage and disadvantage associated with these kind of two devices. So fin height is determined by the silicon thickness. Variation in fin height and thickness is less in SOI FinFET than bulk FinFET. But from the view of economics, bulk FinFETs are cheaper than SOI FinFET. Basic difference is that if suppose we are talking about the fabrication of the SOI FinFET and bulk FinFET, it is very easy to grow the fin over the bulk FinFET, because you have a surface and over that surface you can etch that surface to create a fin, or you can grow some epitaxial up to that height and do that. In general, etching is done. It means the whole of the surface is etched up, etched down, and the fin is directly connected with the surface of the bulk. But if suppose we talk about the creation of the SOI FinFET, you are not getting the silicon surface. Over the SiO2, you have to create the fin. So that is increasing, and the cost as well as some other things will be affected with that. So from the view of economics, bulk FinFETs are cheaper than SOI FinFETs. The first paper on bulk FinFET and FDSOI was given by Hashimoto et al., published in 1990. He used SOI surface and patterned the silicon in the shape of fin over the oxide surface. Intel announced in 2012 that they are going to use bulk substrate to create bulk FinFET, and they used to define the tall fins. When we operate FinFET devices like microprocessors at very high frequencies, heat will generate in the fins. Since silicon is a decent conductor of heat and oxide has 100 times less thermal conductivity, bulk FinFET provide better heat dissipation, because somewhere it is connected with the bulk substrate, and the heat is easily passing to the bulk and it is easily dissipated. While in the case of SOI, just below the fin, there is silicon oxide. So the heat which is generated on the fin will not be circulated to the substrate, and obviously there will be a problem of heat circulation in the case of SOI FinFET. In FinFET device, gate is wrapping around the fin and controls current effectively. But in bulk FinFET, source and drains are connected through bulk silicon underneath and form parasitic BJT, NPN BJT, and some parasitic current can still flow underneath, which is not possible in the case. That is the advantage of SOI, that since the fin is not connected with the bulk, so there will not be any formation of parasitics with the bulk. So control of the current will be more in the case of SOI FinFET. This problem can be reduced in bulk FinFET by increased doping of the bulk area, which helps in removing the parasitic BJT of I off, but it adds the process complexity. It means if we want to reduce the problem of this parasitic formation, we have to increase the doping of the bulk region, and that is obviously going to create the process complexity. Now the last point, which is against SOI FinFET, in bulk FinFET, to create source and drain region, some part of fin is etched at the ends, and source and drain regions are easily created using bulk silicon as a template below. While in SOI FinFET, when some part of fin is etched to grow source or drain region, then no silicon template is left underneath to grow. So that is a problem. You can think that SOI surface is there and no silicon template is there because that bulk part is underneath the SOI area. So how to grow an epitaxial layer if there is no template underneath? So that is also the adding the process complexity. Various parameters, if suppose we try to compare the SOI FinFET and bulk FinFET, so you can think of delta H of fin. It means height variation of the fin height variation, that is less in the case of SOI, but more in the case of bulk FinFET. Cost of SOI FinFET is more than bulk FinFET. Heat dissipation is poor in SOI than bulk. Parasitic BJT formation is not there in the case of SOI, but it is there in the case of bulk. So, and source drain epitaxy is complex in the case of SOI, but easier in the case of bulk. So if we just compare these two, bulk FinFET and SOI FinFET, and that parameter we take that DIBL effect with the gate length, so you can see that a point is there around 50 nanometer. So as the graph, you can see, it is clear that DIBL effect is less in bulk FinFET than SOI FinFET as the effective channel length approaches below 50 nanometer. So you can think of that below 50 nanometer, bulk FinFET is producing less DIBL effect, so it is good. And now we just move on to the fabrication steps of the bulk FinFET flow. So first of all, basis for FinFET is lightly p-doped substrate with a hard mask on the top, and hard mask is made up of silicon nitride as well as a patterned raised layer will be there. So next step that we are etching the silicon area. So fin etch will be there. The fins are formed by highly anisotropic etch process. Since there is no stop layer on a bulk wafer as it is on SOI, the etch process has to be time based. In 20 nanometer process, the width of the fins might be 10 to 15 nanometer. The height would ideally be twice that of or more. In third step, basically, the oxide deposition will be there to isolate the fins from each other. Oxide deposition with a high aspect ratio filling behavior is needed. In the next step, the oxide is planarized by chemical mechanical polishing. The hard mask act as a stop layer. So this is the process. And further, the recess etch will be there. It means another etch process is needed to recess the oxide film to form a lateral isolation of the fin so that we can grow the gate oxide around it. So gate oxide is then grown. On top of the film, the gate oxide is deposited via thermal oxidation to isolate the channel from the gate electrode. Since the fins are still connected underneath the oxide, a high dose angle implant at the base of the fin creates a dopant junction and completes the isolation. Then deposition of the gate. Finally, a heavily doped N+ polysilicon layer is deposited on the top of the film. Thus, up to 3 gates are wrapped around the channel, one on the each side of the fin, and depending on the thickness of the gate oxide on the top, a third gate above can be created. It means if suppose silicon nitride is removed and then gate material is deposited, or the width of the silicon nitride is kept very, very small and gate oxide is wrapped all around, then this becomes a tri-gate simply. So only the top surface, if you are going to utilize the top surface, then it is tri-gate, and if you are restricting the top surface to act or to apply the voltage, then it will be a FinFET or 2D device. So the influence of the top gate can also be inhibited by the deposition of nitride layer on the top of the channel, as I said. Since there is an oxide layer on a SOI wafer, the channels are isolated from each other anyway. In addition, the etch process of the fins is simplified as the process can be stopped on the oxide easily. So basically the oxide deposition must fill a deep high aspect ratio trench, as well as oxide provides insulation between the adjacent fins. The transistors are still connected underneath the oxide. A high dose junction implant at the base of the fin completes the isolation. Also, the fin trench etch simply stops on the wafer buried oxide layer. Because of the buried oxide layer, the adjacent fins are fully isolated from each other and no additional isolation steps are needed. What are the process challenges with the FinFET? Now we have to discuss the process challenges. So everything we do to enhance scaling in the present day scenario involves a lot of compromises in device level. A lot of trade-offs are required. So here we will discuss about the issues in processing point of view in the making of FinFET or the 3D transistor, that is tri-gate transistors. So FinFET are 3D devices and they involve edges and corners to transport charges, and this brings in a lot of challenges. Gate dielectric wraps around the fins, so it has to be conformal. Similarly, gate metal has to be conformal, and a lot of process challenges are related with the conformality of the gate material. Similarly, when we make source and drain region, the metal should be conformal around source and drain region. So there are many process challenges, but we will talk about those process challenges that are related with the 3D nature of the FinFET devices. So first process challenge is the corner effect. So you can think of this as related with the physics, that if suppose current or charges, mobile charge carriers are moving from one side to another side, and there is a structure like fin, suppose, then most of the current density you can find that is lying around the edges and the corners of the device. So whenever we have a constant surface potential, the electric field is amplified at the corners than the edges. So we have much larger electric field at the corners, and same phenomena applies to the fins, such that as we apply gate voltage, more electric field at the corners, and because of that much larger population of the electrons at the corners as compared to the side walls, so that is going to create the problem. Problem means there is no uniform distribution of the electric field. So as we are increasing the gate voltage, surely you can think of more disruption will be there towards the corners and the edges. Center will be always protected or same. So if we plot current density at the gate voltage near threshold voltage, then we find that due to higher population of electrons at the corner, the current is still conducting, which is bad for FinFET. Means even at a very small gate voltage, there will be a very small current flowing through the corners and the edges. Because of corner effect, device turns on even at a gate voltage lower than the threshold voltage. Or in turn, we can say that the threshold voltage decreases because of the corners. So both of the other way around, we can say. So unique advantage of making FinFET was its subthreshold slope, but because of the corner and edge effect, the subthreshold slope degrades, and we have multiple VT points. So you can see with the figure that the current versus VGS graph, as the plane of FinFET or the ideal FinFET we talk about, in middle there is producing, or which is displaying that there is some variation because of the corner and the edge effects. To resolve this problem, basically earlier the edges, or you can say the fin, was rectangular. To resolve this problem, the above surface of the fin was slightly rounded, or the edges are also tapered. So one way to solve this problem is to round off the top surface of the fin, take the fin and anneal in hydrogen environment and hydrogen anneals, and tend to round off the corners. Another option is to take tapered fin, and you don't get any corners at the top. So in fins, we have the constant width, what we are rounding or off or taking tapered fin, then width is essentially changing along the fins. This can solve the problem of the corner or edge effect, but it is again posing other kind of problems. So device threshold voltage as well as electrostatics are very much sensitive to the width of fins. So having multiple width along the height of the fin is not a good option. Also, when we are rounding or tapering the fin, then we are basically changing the crystalline structure of the surface. It means the above surface may have, it means the rounding or tapered surface may have the different crystalline structure, and that is going to change the desired behavior of the device. Now, if we use thick nitride at the top and wrap gate oxide around over fin, then we are actually not using top surface, and corner effect will be minimum, and this is ideal 2D device or FinFET device. So in general, if we are using the tri-gate devices, then this problem is severe in comparison to the ideal FinFET devices. all these are different approaches to avoid corner effects. Next problem is shadowing. Another problem is related with the creation of source drain region. So when we are creating heavily doped source and drain region in the planar transistor, we require halo implant, and source drain extension implant. But the problem comes with the 3D nature of the fin. So when we are creating fin, we need to dope the fin with required concentration of dopant, and we require uniform dopant concentration in the fin. But since the fins are basically lying nearby, so whenever we are just implanting or doping, creating the dopant region, then obviously one fin is going to act as a shadow for the another fin. So that is posing a problem. So we need to flow the dopant from all the directions, but in reality there are multiple fins created over the surface of the wafer, and are N-type or others are P-type. So when we are creating P-type fins, we need to cover N-type fins, and when we are passing the dopant over the surface, it is not penetrating equally from all the direction, and this term is termed as shadowing. So summary: the FinFET was originally developed to manufacture self-aligned double gate MOSFET to address the need for improved gate control to separate off current, I off current, DIBL effect, and process induced variability of gate length less than 25 nanometer. Tri-gate and bulk variation of the FinFET have been developed to improve manufacturability and cost. It has taken 10 years to bring 3D transistors into volume production. Multi-gate MOSFETs provide a pathway to achieve lower power and improved performance. And further evolution of the MOSFET is to be stacked channel structure may occur by the end of the roadmap. Thank you. If you have any query, any question, your
काय म्हणजे डेट नुसार नाही आता कसं ऑक्टोबरचे कोणकोणी 30 तारीख दिलेली हा मग 30 तारीख मी आता टाकणार म्हणजे मी सांगितलं नाही 13 ला देणार आहे की 12 ला देणार होती
Any questions? So thank you.
Hello, sir. How can we hack the Wi-Fi password? Hello, can we have the answer, sir? We have the query. Question. Hello, sir. Listen to me. Hello, everyone. Anyone can help us, sir? Meeting. अरे Wi-Fi का password. Sir, one question, sir, please. Hello, listen to me. Hello, sir.
Yes, please.
Sir, how how we can password Wi-Fi and the password. So we have to time. How can hack the password of PC?
I think so. It is irrelevant question.
Yes, sir.
I think so. It is irrelevant question with the technology we have discussed. We have discussed about the FinFET technology, and you are asking about the password setting of the computer. Any other question from any other center?
Good afternoon, sir.
Good afternoon.
I'm Anup Sarkar from MRU.
Fine.
Sir, just now in case of FinFET, we are using only a single oxide, no, sir?
One.
We are using only a single oxide.
Fine.
Between sir gate channel, we are using single oxide. Am I audible, sir?
Your voice is not coming to us properly.
Sir, actually, what I am saying that we are having only one type of oxide.
What?
We have not
One type.
between and channel. We are having only one type of oxide.
In channel, we are not having any oxide. Oxide is wrapped around the channel.
Yeah, that I think can be increased number of layers. Means we can use different K type or high K dioxide, high K oxide, and all these things.
Okay, okay.
Does it means it has been fabricated or not? Means we have used only single oxide.
Okay. One point is there that this thing that we have to talk about two things. Number one, if we are talking about the only FinFET device, then in FinFET device, basically we are having two types of oxide. One is wrapping the channel to form the gate oxide, and another type of oxide is isolation oxide. So these two oxides are slightly different, you can say, parameters. That gate oxide has to be very, very heavily pure oxide, because you are applying some gate voltage, and that is going to control the flow of the current in the channel. So that oxide has to be very, very pure, and in general thermal oxidation is used to produce such kind of oxide. But in case of isolation oxide, we do not require that the heavily pure oxide has to be there, but we want that oxidation growth rate has to be very fast. So that can be any other kind of technology, anodic oxidation or another kind of oxidation can be used. That is related with the FinFET. But in earlier previous lecture, we talked about that we can have other high K metal gate.
Yes.
Fine. So in case of high K metal gate, if we talk about, basic point is that as the technology is increasing, the gate width is also decreasing. We have to decrease the gate width as the device size is shrinking. So when we are decreasing the gate width, obviously you can think of that separation between the substrate and the above metal is also decreasing. So you can think of the capacitance. Capacitance is basically depending upon Ka epsilon upon D. If D is decreasing, obviously the capacitance part is increasing. One point. Another point is that the electrons which are moving in the channel, if they are very highly energetic, they may penetrate through the oxide layer. If suppose we want to decrease that parasitic gate capacitance, we have to increase the value of the K of that capacitance. It means Ka epsilon upon D. So if D is decreasing, we have to increase the value of the K. So if K is increasing by using another material, and if we suppose can fabricate such kind of material over that, obviously that is a good choice. So for that we are choosing other hafnium oxide or zirconium oxide as a metal gate technology. Yes, please, if you have other any other point.
No, sir. Thank you so much, sir.
Welcome. Any other center is having question? ठीक है, thank you all.
So I request all the centers, we will have a validation session at 12 p.m. So please get ready for your validation session. We will assemble at 12 p.m. Thank you.
They should marry each other.
अनुष्का शेट्टी 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 ना तेलुगु इटा आप मूलठू आप देखो आप बॉलीवुड जी फेमस हो आप टॉलीवुड से फेमस हो एनटी रामाराव हो कथा हूँ एनटीआर समझे सब चिरंजीवी फिल्म लाइन से जहाँ भी हो जहाँ भी से सेलिब्रिटी ये बहुत भल ये तेलुगु इंडस्ट्री तेलुगु नेक्स्ट तमिल बोधे आसो तमिल मत एडवर्टाइजमेंट सब अधिक
Good afternoon, all the centers. So myself, Garima Seni, I am Assistant Professor, Electronics and Communication Engineering Department. Dr. Rajesh Mehra was on official tour. He has to go to urgently for official tour. So I will be validate this course on VLSI Design. So now I request all the centers one by one about their feedback of this course. So Government Polytechnic Kaladungi. Government Polytechnic Kaladungi. हाँ जी sir.
Regarding the course which I have get the course, it's too much informative, and when it's come to the grade, I will grade it good.
Thank you, sir. Any other feedback from your center?
Being a very remote area, we have managed, and thank you for choosing this as a nodal center. And in future, we'll try our level best.
Okay, thank you so much. Now I request Sobha Saria Group of Institution Seeker, Mr. Rakesh Kumar, the course coordinator of the center. Sobha Saria Group of Institution Seeker.
Ma'am, he is unavailable right now.
So anybody can give the feedback, ma'am, regarding this course?
Ma'am, it's a very useful, and we really feel very regarding that it's a too good for us and all the teachers as well as.
Okay, thank you. Rakesh sir will be available
in few minutes, ma'am. In few minutes.
Okay, then we will come back to you. Thank you. RIET Jaipur. Aditya College of Engineering and Technology. Then ARIT. ARIET. ARIET Mumbai. I think there is some problem with these centers, connection problem. Now IGDTU Delhi. ARIT Mumbai. Mr. Ashish. मानव रचना को बुला लेते हैं यूनिवर्सिटी या वो इंटरनेशनल यूनिवर्सिटी फर्स्ट वाला मानव रचना यूनिवर्सिटी फरीदाबाद
हेलो मैम am I audible?
हाँ जी मैम प्लीज
Good afternoon to everyone. I'm Yogita from EC department. I'm working as assistant professor here. Actually, this training really proved to be a benefit for our college because we are also going to start a new course on VLSI and embedded designs. And special mentions to Rohit Sharma sir and KG Sharma because they gave wide knowledge about newer technologies that is being used today. And thanks from all of us. It was a really good course.
Okay, thank you so much, ma'am. Any other feedback from your center? Okay, now Gandhi Engineering College, Odisha. IGDTU, Delhi. IGDTU, Delhi. ABS Engineering College, Ghaziabad.
Am I audible, ma'am?
हाँ जी sir.
Yes, ma'am. It was very nice FDP, and we learned a lot from this again. From this FDP, as we have already learned in the previous FDPs from you also, and it was of much use. However, I want to say that it would be little better if we can give focus more on some tools.
Okay.
As we learned from TCAD, etc. If we can give more emphasis on that, it will be much better.
Okay, sir. I will give your feedback to the course coordinator. He will look after this. Thank you so much. Thank you, sir.
Hello, ma'am.
Hello.
This is Ashish Kodwe from Mumbai.
हाँ जी sir.
From RMIT Engineering College.
हाँ जी sir.
I'm very thankful for this from NITTR. Actually, this course is also run in our Mumbai University.
Okay.
And I'm also thankful to Dr. Rajesh Mehra sir and all the team of NITTR course runner. And I want to suggest one thing.
Yes, sir.
Basically, we are expecting any tool simulation over the course, but still Rajesh Mehra sir has covered the ED tool, but we expected more in depth in simulation part.
Okay, sir. I'll communicate your feedback to Rajesh sir.
Am I audible, ma'am?
Yeah, yes, sir. Sir, we will consider your feedback for the next course. Thank you so much. Yari college कौन सा है last? Not 10th number पे नारा सारा पेटा इंस्टीट्यूट कहाँ पे है ये? आंध्रा. नाम क्या है यार इस कॉलेज का? Nara Sara Opeta Institute of Technology, Andhra. Hello.
We are from Nasapa Institute of Technology.
Yes, sir. Yeah, it's audible, sir.
Yeah, we feel very happy, ma'am. Even though they are experienced students, they are providing each and everything from basics onwards, from ABCD onwards. They are receiving nice manner with the participants are so this type of culture is very important. The faculty, especially, they are very happy in the classes. The students will benefit so much. So we feel very happy with this. And next, we are providing this type of lectures in online. Others will also get seen. We will inform the others also. Some of them are missing this type of lectures. Whatever this is, they are posting and posting in online. Others will also benefit so much. Is it audible now?
Yes, sir, but there is so much noise, I think, at your center.
No nice, ma'am.
Okay, sir, I'll thank you for your feedback. Oh, thank you. Gandhi Engineering College, Odisha. Manav Rachna International University.
Hello, good afternoon, ma'am.
Good afternoon.
Ma'am, we at Manav Rachna International University express our heartfelt thanks for organizing this ICT-based online program on VLSI design. Throughout this week, ma'am, various informative lectures were conducted, which covered various topics from CMOS design to design optimization to device simulation. A special thanks to Dr. Rakesh Mehra for organizing this particular ICT program. Lecture from Dr. Rohit Sharma on high-speed interconnects and graphene nanoribbons in particular was quite informative, as it is the latest topic of research in VLSI design. So again, I would like to thank you for providing us a platform to enhance our knowledge, and hope you will continue to provide us with such more platforms or new technologies in future. Thank you so much, ma'am.
Thank you, ma'am. Thank you for your feedback. Aditya College. So thank you all the centers for having giving this opportunity to NITR to be the course coordinator center for all this course VLSI design program, and I'm hoping that we will have you as a center for other courses also. You can look at our O plan of the yearly O plan for ICT courses and even in the contact mode courses also. So thank you all. And on the behalf of EC department, I would like to thank ETV department and Deepika, especially because she is handling this course from the last 5 days. Thank you.
Thank you.